the world's most important metals, aluminium. Our story starts here in the Republic of Ireland. Bauxite, impure aluminium oxide, arrives at Auchinish on the Shannon estuary. The ore may have come from many different parts of the world. This came from northwest Africa. There are also major reserves in Jamaica, Central America, Australia. It's stored in these giant buildings, ready for the purification process. The roof's a lightweight structure. Its slope exactly parallels the slope angle of the great mountain of bauxite inside. To purify the bauxite, it's first treated with hot sodium hydroxide solution in these giant pressure vessels. Let's look at what happens on the laboratory scale. In the beaker, we put some bauxite, impure aluminium oxide, and we heat it up with sodium hydroxide solution, a strong alkali. Now, aluminium oxide is amphoteric. It acts both as an acid and as a base, so it dissolves in the alkali to form a salt, sodium aluminate, but the impurities are not affected. Filter, and the sodium aluminate solution passes through the filter paper, leaving the impurities behind. If we now acidify the filtrate, the sodium aluminate is decomposed and pure aluminium hydroxide is precipitated. This pure white aluminium hydroxide can be filtered off and heated to produce pure alumina, aluminium oxide. In the plant at Auchinish, the aluminium hydroxide is precipitated in a different way, in these huge tanks, but the principle is the same. The aluminium hydroxide is heated to produce pure alumina, and this is carried out to waiting ships. Now, in the lab, the impurities from the bauxite were left on the filter paper, mainly iron 3 oxide. Industrially, vast tonnages of this red mud are produced, and at Auchinish, this is spread in huge lagoons over a layer of tough plastic sheeting so that the environment around is not polluted in any way. In fact, there's a nature reserve right next to the lagoons where many water birds breed. Leaving the red mud behind, let's follow one load of the purified alumina to Holyhead on the Isle of Anglesey in North Wales to see how metallic aluminium is produced from it. The fine white powder is removed through powerful vacuum pipes. 200,000 tons of alumina a year arrive here, some from Ireland, some from other sources. It's carried by tunnel to the Anglesey aluminium smelting plant. How can we produce aluminium from this oxide? The important thing to understand is that aluminium is a very reactive element. You can see this if you take fine aluminium powder to a Bunsen burner flame. It burns very fiercely to give the oxide. Bigger pieces of aluminium don't burn, which is why we can use, for example, saucepans made of the metal. The point is that the metal carries a hard, thin coating of its oxide, which stops it burning. If this coating is removed, then you can watch the aluminium spontaneously changing into the oxide as it reacts with oxygen in the air. Metals which aren't very reactive are fairly easy to produce from their oxides. For example, you only have to heat up mercury-2 oxide for it to split up into mercury and oxygen. You can see metallic mercury condensing on the side of the test tube. Mercury-2 oxide decomposes on heating to give metallic mercury and oxygen because mercury is not a very reactive metal. Copper is slightly more reactive. If we heat copper-2 oxide, it does not decompose, at least not using normal laboratory methods. We'll flush out the air with nitrogen. Perhaps you'll see why in a moment. We'll now pass hydrogen over the heated copper oxide. Watch what happens. Very soon we can see metallic copper being produced. There it is, in the middle of the boat. Hydrogen is more reactive than copper and reduces the copper-2 oxide, taking the oxygen away to form water and leaving the less reactive copper. Now, if we try this with aluminium oxide, nothing happens, at least not under these laboratory conditions. Because aluminium is very reactive, it hangs on to the oxygen and no metal is produced. The aluminium oxide, alumina, is completely unchanged. So how can we get aluminium from its oxide? The answer is by using electricity, by electrolysis. This is an electrolytic cell for producing aluminium. Let's look at how it works. This is the end view. There's a steel shell lined with carbon blocks. Blocks of pure carbon mounted on metal rods dip down into it, and it's filled with cryolite, another aluminium compound in which the alumina is dissolved at 970 degrees C. The cell and lining blocks are made the cathode, negative, the carbon blocks the positive anodes. At the anodes, oxide ions give up electrons and become oxygen gas. At the cathode, positive aluminium ions pick up electrons and are reduced to aluminium metal. So molten aluminium collects at the bottom of the cell, and when enough has accumulated, it can be run off. The process is a continuous one, and the cell is never allowed to cool down. Here are the massive electrical connections to the cathode and to the anodes. There are 18 anodes to each cell. The whole plant at Anglesey Aluminium uses enormous amounts of electricity, a current of 145,000 amps, with a voltage drop of about 4 volts across each cell. There are 308 cells, each producing aluminium in 4 enormous rooms, consuming 200 megawatts of power. This is just part of one of them. As the dissolved alumina is separated into aluminium and oxygen by the electrolysis, fresh alumina has to be added. Hoppers on top of each cell are filled from this giant overhead conveyor. Each cell is controlled automatically. The crust, which forms on top of the electrolyte, has to be broken before shots of fresh alumina are dropped in from the hopper at the top. Under the top layer, the electrolyte activity takes place. The molten electrolyte bubbles. The carbon gradually burns away in the oxygen liberated at the anodes, forming carbon dioxide. So each anode has to be replaced about every 3 weeks. Here are the remains of 2 burned up anodes being removed from a cell. What's left of the anodes is broken off to be used again in making new ones. To make new anodes, pure carbon from petroleum refining is mixed with pitch and the remains of old anodes and compressed into blocks. Each block is carefully checked for size. Here are some anode blocks waiting for the next stage. A lot of the space occupied by the Anglesey aluminium plant is taken up by anode production. 300 pairs of anodes are changed every day. They're baked for 18 days in great underground furnaces. Then they're almost ready for use in the cells. But first, they're sprayed with aluminium. What do you think this might be for? Here are new anodes, awaiting their turns to be taken to the cell rooms. They're fitting one into a cell. First, the crust has to be broken. Down it goes into the hot electrolyte. Here are the roofs of the 4 long cell rooms. It's important not to allow any harmful fumes out into the atmosphere, and all the gases and vapours produced by the cells and during the baking of the anodes are carefully filtered and purified before they enter the high stack which releases them into the atmosphere. Approximately 1 ton of aluminium is produced in each cell per day. This is drawn off by a vacuum tube into a crucible. This holds about 5 tons of liquid aluminium at over 900 degrees C. It's poured into holding furnaces where it's kept molten. Other elements can be added to produce aluminium alloys for various uses, such as iron, silicon, manganese, magnesium. The liquid is stirred using a special stirring block suspended from a crane. If you watch carefully, you can see where some of the aluminium burns. The slag floating on top consists mainly of aluminium oxide and aluminium nitride, and it's scraped off. This is one of the gas jets keeping the metal hot. The molten alloy is poured into moulds to produce what are called sows. The melting point is about 630 degrees C, and it quickly solidifies. Each sow weighs 500 kilos, half a metric ton. Smaller pigs are also produced, each weighing 50 kilos. Sows and pigs are sold to customers who remelt them to make whatever articles they want to produce. And by a process called continuous casting, these are produced. This is a rolling ingot, weighing 10 metric tons. Many articles can be fabricated from it. The aluminium in its various forms is stored until lorries take it to customers throughout the country. This smelting plant produces 100,000 metric tons of aluminium every year. Aluminium has very many uses. It can be used in buildings, aluminium handrails, aluminium door frames, aluminium window frames. Aluminium alloys are used in the aircraft industry. Something very different, cooking foil. And aluminium is a very good electrical conductor, and its density is low, so it's used, for example, in electricity cables. Here's a very different use of the metal. This is aluminium powder. This is iron 3 oxide. Neither of them is magnetic. If we mix aluminium powder and iron 3 oxide and ignite it with a fuse made of magnesium ribbon, taking the necessary precautions, watch. There's a very vigorous reaction, generating a lot of heat. Cool it down. A lump of metallic iron has been produced. See how it's attracted by the magnet? Aluminium is more reactive than iron and takes away the oxygen, forming aluminium oxide and metallic iron. This would be far too expensive a way of producing iron, but it can be used when intense heat is needed to weld metals together. Steel railway track is the best example. The mixture is called thermit. When it's ignited, the aluminium reduces the iron oxide, takes away its oxygen, and great heat is produced, this time on a bigger scale than we used in the laboratory. Pull the plug out and hot iron falls onto the gap in the rails. The rails have been welded together. This isn't the most important use of aluminium, but it reminds us what a very reactive metal it is. That's why it must be won from its ores using electrical energy, as you've seen in this film at home.
How many we have, Link?